Welcome back, Professor Bright here, and we're going to look at a couple applications with dot product. The first one that we're going to look at is vector projection. And so to begin, I just want to start with looking at two vectors. So let's say we have two vectors that share a common initial point. Maybe here is vector B. Let's call this vector B, and then here we're going to call this longer one vector A. Okay. Now what we want to do is look at how far along vector B extends along vector A. So that is to say, if we could think of a sun that is right above, that's a bad sun. Okay, so we have still a bad sun. Well, you get the point. If we have a sun right above the tip of B, it would be kind of casting a shadow down along A, and I'm curious about how far the shadow would extend. Okay, so let's think about this a little bit more. So we can, or by our geometry understanding of vectors, or of dot product now, I could look at the angle between them, right? Dot product can help me answer that question. And for all intents and purposes, I can think of this shadow. Oops, let's redo that. Undo. There we go. Let's call that shadow length from here to here. Let's call that D. Okay, and it will have a direction and all that, but I'm just concerned about the length. Okay, so I want to find what D is. Okay, now we also notice that this is a right triangle, so I can say, okay, well, if I want to find D, right, I can say that that is related to, okay, I can use cosine to find that, so let's do cosine of theta is equal to D over the length of vector B, right, or the magnitude, rather. Okay, so if I want to find D, that's easy peasy, so multiply by magnitude of B, so I get D is the same as magnitude of B cosine of theta. Okay, that isn't bad. But wait, I know what cosine of theta is according to the geometry, right? I can say that this is the same as, okay, so this is vector B, okay, this is going to be A dot B over length of A, length of B. Okay, so then if I simplify this, this is just going to be, right, that would cancel, so I'd have A dot B over length of A. And so this, we have a name for this in mathematics. I'll write it, but you don't need to know it. It's going to be the component of vector B that is along vector A. So that we call it the component of B along A. Okay, but that's not actually where we stop. What we would actually say is that if we were to project vector B along A, okay, it would be the component of vector B along A in the same direction as A, so that would be, so we kind of think of this as the multiple of it, but then we need to take vector A and make it into a unit vector. Okay, so when all is said and done, the projection formula, if you will, ends up being A dot B over, and then we had length of A twice in the denominator, length of A squared, all times vector A. Okay, so in terms of, if you have to remember a certain formula for projection of a vector, so again, projecting B onto A, this is the formula that you will need to remember. Okay, so now let's put that to use. Okay, and I have that. I called it B1 here, and D above, that's totally fine. Okay, here we go. So here's a vector. We want to find the projection, and then we want to find vectors V1 and V2 such that bunch of scary stuff. Okay, let's worry about A. So I want to find the projection of W onto V. So by definition, this is going to be V dot W over the length of the projected, or the vector we're projecting onto, so it'd be length of w, times squared, and then vector w. Oops, no square there. So then, let's find the dot product, so this ends up being this after you do all the math, okay? Now, for part B, it says find vectors v1 and v2 such that v1 is parallel to w and v2 is perpendicular. Okay, so parallel and perpendicular respectively, and we want the two to sum to v. Okay, so that idea is very similar to what I drew above. So if you can imagine, I'm not going to draw this to scale necessarily, but we have vector w that we're projecting along, and here's vector v, right? What I want to do is find a vector v1 that is parallel to vector w, right? And then I want to find a second vector that is perpendicular to w, but when I add the two, I get to the same spot as v. Okay. Now, technically, we've done some of the work already. In part B, v1, right, that if we project v onto w, that projection is just v1. So this is the projection of w onto v1, or onto v, or sorry, v onto w. I read that wrong. So this is just minus 0.2 minus 0.6. Okay. Now for v2, that one's a little trickier. Okay, we want to find something that's perpendicular that gets us to the same spot. Okay, so this one I don't know quite so much, but I'm gonna be clever. I'm gonna cheat. I know that v1 plus v2 is equal to v, right? That was given. So, well, I know what v1 is, I know what v is. Oh, I can just move it to the other side, solve it like an equation. v1 or v minus v1. Oh, that's pretty easy now. So v was 7 minus 3, and then I want to subtract minus 0.2 minus 0.6, and if I do all that, I end up with if you write it in fraction form, it's going to be 36 fifths and negative 12 fifths. Okay, so I found my two vectors. Okay, so big idea that we wanted to pull out here was that the projection vector is in the direction that is parallel to the vector you're projecting onto. Okay. Now this next question is a little bit of a challenge question. I want you to do your best with it, and then I will pause and I'll show you the solution once you've done it, and I'll briefly explain it. Here's the solution. So there were a couple key things to keep in mind. First, we need to represent this as a picture, right? But when you do, you need to represent this 5-pound force as a vector. Okay, so that's here. So it's 5 units down in terms of weight, so there you go. Then the other thing is when you're setting this up, the perpendicular and parallel components, we have to do that relative to the ramp that we're on, not relative to kind of where the horizontal would be. Okay, so just keep that in mind. Okay, once you get all that set up, the other thing you need to do is when we're projecting, right, we want to project vector F along the hill, right, or the ramp. I should have said ramp here. But that vector, we call it v. It would, if we just think of it as magnitude of 1, that 1 is a little bit arbitrary. It actually ends up not mattering at all. But for ease, we put a 1 there. And then in terms of the direction, we would say the direction would be cosine 5 degrees, sine 5 degrees. So really v is just cosine 5 degrees, sine 5 degrees. And then from there, once we get really everything to the left of this line setup, then the rest of the math kind of follows what we just finished in the previous exercise. So have a look through that.